I had said before that the dynamics of the ocean circulation and the atmospheric circulation produce these patterns of warming, and we have been repeating a few times that the polar regions are warming faster. It's not so obvious here, but you can find, remember also there is always a data issue in Antarctica, but the latest figure, if you go look for it, well, this is quite the latest, you will see that even Antarctica is warming faster. So there are some regions you can see are warmer than other regions. Okay, so we have to make a few points here. The high latitude warming that is larger is called polar amplification. This is the buzzword or the scientific term for how the ice albedo feedback at higher latitudes will actually produce more warming. And in a very first order sense, you can also remember that the tropics are warmer. I have repeated this already a couple of times, but it's worth listening to again. If you try to warm the tropics, which are already warm, the evaporation will increase. Atmosphere is warm, it's holding more moisture, so you will increase the convection or the circulation of rising air, expanding air, convection, rainfall, hitting the ceiling, going in Walker cell and Hadley cell, and so on. So there are changes in the Walker cell, and there are changes in the Hadley cell because of the warming as well. There are some details like how much energy you can lift from the surface depends on how thirsty the atmosphere is. If you keep filling the atmosphere with water vapor because it's warmer already, then the amount of water you have to lift changes, and then the way the rain falls also will change. Why? Because you can think of it, the atmosphere as a sponge. If you keep pouring water on a sponge, it'll soak water and get wet, saturated all over. But then if you push on the sponge, the water is not going to drizzle, it's going to start pouring at some point, okay, based on how the pressure is applied and how the water gets pushed to one side and falls down. So the atmosphere is like a sponge which is soaking up water, and the pushing is coming from the instabilities that produce rain. The regions where rapid rise happens, convergence happens that we talked about, like the West Pacific, the Indonesian seas, Indian monsoon during the monsoon season, Amazon rainfall, the ITCZ. So that heavy rainfall when you push the sponge is called extreme rainfall. So rainfall doesn't just come as a drizzle everywhere, increased drizzle because of global warming. It'll start to pour somewhere. And remember, the moisture is being supplied. Like we said, subtropical gyres are clear regions, high pressure. They are evaporating and supplying the moisture to the rising regions like the ITCZ through our Hadley cell convergence near the surface, right? There's divergence at the top. So these kind of details are involved in how the dynamics and the thermodynamics of the system works. What is thermodynamics? Dynamics is the circulation, the winds, the water vapor transport, clouds moving everything. Thermodynamics is this water vapor evaporating, condensing, moving energy, and so on. So dynamics and thermodynamics together determine these responses. Now you can also combine your knowledge of ocean circulation to see where ocean would take down the heat that is coming at the surface. As I said, the diffusion process is very slow. That's not very critical. So if you look at the climatological structure, you know that the tropics are warm. This is some kind of a zonal mean meridional section again, and you can see where there is subtropical gyres, there is convergence, water is going down. So you can see that warmer, lighter waters are pushing down deeper where the subtropical gyres are. So it's like a funnel where the convergence is happening. So the upwelling is wiped out here because we averaged over the warm waters and the cold waters. And at high latitudes you have mixing down, no thermocline, so you have cold waters all the way down, right? So you can see that structure here. The scale changes here. This is from 0 to 500, and then this goes from 500 to 2000, just to show you the deeper ocean. So when you begin to put heat at the surface, it is this convergence, deep water sinking, etc., that begin to favor where the heat goes down. So you can see now the trend in potential density. It's getting lighter. It's negative. It's getting lighter because it's getting warmer. And there is rain as well in some places, making it fresher, reducing salinity, which also reduces density. So subtropical gyres are obviously penetrating the global warming heat to much deeper depths, because that's where surface waters can converge and take the heat down. And here is our favorite place at 60 North, where we have the North Atlantic Deep Water Formation. Okay, so you can see that the heat is going down there as well. It takes down carbon dioxide, heat, other gases, everything. Remember the oxygen profile? It had a minimum in the oxygen minimum zone, and that increase again. It's this sinking water that's taking the surface oxygens down and increasing the O2 in the deeper waters. So the main thing to remember is that the dynamics of the ocean, which is still related to Walker cell, Hadley cell, trade winds, westerlies, polar easterlies, and so on, it's still got the circulation, and that circulation takes down, it's called advection, so the heat is advected, which is much faster time scale than diffusion. Diffusion is a very slow process. So this is a nice Southern Ocean centric view. Here is the channel of the Southern Ocean with its circulation, east to west in the outer part, east wind drift in the inner part, and you can see Southern Ocean is warming and penetrating pretty deep. Why? Remember that Southern Ocean is an open channel where the wind can keep on putting more energy than other oceans, because it's an open channel. So the heat can penetrate deeper and deeper with the Ekman currents, the wind-driven currents. And it's that water that can then go into the Indian and Pacific Oceans. Okay, so Indian Ocean, Atlantic Ocean, and again you can see the Antarctic deep water, bottom water, etc. here. You can see the North Atlantic deep water here. Indian Ocean has its own meridional overturning, as we know. Deeper waters come in, become surface waters, and come out. So the warming patterns in each ocean is going to be related to the dynamics. This is what you have to remember. So the ocean warming patterns below the surface are not just going to be a slow diffusion down from the surface, but it's going to be very fast and deep in some places, and shallow in other places, maybe even a cooling in some places, because the thermocline gets lifted in some places, gets pushed down in some places. Surface cooling can happen in some places, which means the sea level rise is also going to be having a pattern that's not just sea level is rising everywhere. There are some places where sea level is rising faster, like the northern Bay of Bengal, where we said the sediment load from the Himalayan rivers is pushing the land down, and we said off of the east coast of the US, dynamics is changing, plus the gravitational pull of the Greenland glacier is decreasing and sloshing the water back. So again, 1 + 1, but you have now many ones. You have many concepts that you have to carry in your head and keep combining them as and when necessary. Stare at these figures and keep remembering your basic concepts to make sure that you can make the links. They are still fairly straightforward, but it's just that you are to carry many pieces of information and you have to be able to synthesize them properly.